Hi everyone, this is Dr. Ranjani. Today's topic is application of Schrödinger wave equation particle in a one-dimensional box. I'm going to draw a one-dimensional box here. Here, one dimension is the length of the box or the width of the box. Let A be the width of the box. Consider a particle X of mass m moving freely only along the x-axis inside this potential box of width A. Here inside the box, I am taking the inside the box as region 1. The potential energy of the particle is 0. And region 2 outside the box. Here it is region 2. And this is inside the box region 1. These are outside the box region. It is x-axis. Outside the box, the potential energy is infinite. Even at the walls of the box, the infinite potential energy. So, region 1 denotes inside the box and region 2 denotes outside the box as well as at the walls of the box, at the walls where the potential energy is infinite. The width of the box is A and mass of the particle is m. Now, the potential energy is V is equal to 0 here inside the box, and it is a freely moving particle. Even the particle collides with the walls of the box, but there is no loss of kinetic energy as the particle is subjected to elastic collisions. Now, the position of the particle inside the box can be written with x greater than 0 but less than A. You can see from the diagram here, the position of the particle x is greater than 0. It is greater than 0 here, but less than A because it is inside the box. Whereas outside the box and at the walls in region 2, you can make this as x is less than 0 but greater than A. Therefore, x is less than 0 greater than A. This is about outside the box. Even at the walls, x is equal to 0, x is equal to A. Therefore, we can write this as x is less than or equal to 0, greater than or is equal to A, where the potential energy is infinity, and we are going to apply the Schrodinger's time independent wave equation because the particle will be continuing in its one-dimensional motion that is independent of time. That is independent of time. So Schrodinger's one-dimensional time independent wave equation is d square psi by dx square plus 2m by h cross square E minus V psi is equal to 0. Since the potential energy of the particle inside the box is 0, this can be rewritten as d square psi by dx square plus 2me by h cross square psi is equal to 0. Here, since we have got only one-dimensional motion, only ordinary differentiation is taken. Now, for the second order differential equation, we need to get a solution. Even this equation can also be written as d square psi by dx square plus k square psi is equal to 0. I am going to take this as equation 1, and k square is here 2me by h cross square. K square is taken as 2me by h cross. Let this be equation number 2. Now, the solution of this equation, I am going for solution of equation 1 as the solution of this second order equation as psi of x is equal to a sin kx plus b cos kx. This can be taken as equation number 3. Now, we know the boundary condition is x is equal to 0. Here, the boundary condition for the particle, the boundary condition is x is equal to 0 at one wall. Do you understand? At one wall, it is x is equal to 0. And at the other wall, it is x is equal to a. When it is making collisions, it is acting as a particle. Therefore, the wave function will be taken as 0 even outside the box as well as at the walls also. So, a is equal to 0 here. Now, applying boundary conditions here. The first boundary condition is x is equal to 0. Now, wherever you see x, you are going to write 0. Applying boundary condition when the particle x is at 0. At the first boundary condition, k of 0 plus b cos k of 0. Here, a and b are called as arbitrary constants. A and b are called as arbitrary constants. What is the value of psi when it is at the first boundary condition? When it is at the first boundary condition, here at x is equal to 0, it is psi of 0 becomes 0 because the particle will act as a particle at the wall, not as a wave. Therefore, the wave function value is 0. Sin 0 is 0. Therefore, the first term vanishes. Cos 0 is 1. Therefore, we have b value. So, the arbitrary constant b is 0 here. Now, applying b is equal to 0. B is equal to 0 in equation 3. In equation 3, we get psi of x is equal to a sin kx plus b is equal to 0 cos kx. So the second term becomes 0. We get psi of x is equal to a sin kx. Let this be equation number 4. Now we have second boundary condition. Boundary condition 2. Boundary condition 2 is x is equal to a. So boundary condition 2 is x is equal to a. So this is second boundary condition and this is first boundary condition. Now applying x is equal to a as well as the arbitrary constant b is equal to 0 in equation 3 as well as b is equal to 0 also in equation 3, we get psi of a, x is equal to a and b is equal to 0. A sin ka plus b as 0 cos ka here. So what is the value of psi of a? Even at the second boundary condition also. In the diagram you can see here, even at x is equal to a also, the particle has no wave function because it is not moving, it is just colliding, it is acting as a particle only at the walls boundary conditions. Therefore psi is equal to 0. Now we get psi of a as 0, a sin ka, it is 0. Second one vanishes. Now we are looking into these two. A and sin ka, the product of these two becomes 0. Already one arbitrary constant is 0, b is already 0, so we cannot take a, the other arbitrary constant, as 0. But the product of a sin ka is 0. Therefore, sin ka must be taken as 0. Whenever the value of ka is equal to n pi, then only we can get sin value of ka becomes 0. Therefore, k is equal to n pi by a. Let this be equation number 5. Now, we are going to square this. K square is equal to n square pi square by a square. Let this is equation number 6. Now, can you see this equation 2? K square is equal to 2me by h cross square. Here in 6th equation, k square is equal to n square pi square by a square. I am comparing these two equations. Comparing these two equations, we get, that is, I am writing it, comparing equations 2 and 6, we get 2me by h cross square, where h cross is the reduced Planck's constant, here. And 6th equation is n square pi square by a square. Now the reduced Planck's constant h cross is equal to h by 2 pi. H cross square is equal to h square divided by 4 pi square. So I am substituting h cross square as h square by 4 pi square, which is equal to n square pi square by a square. I am rearranging this equation. 2me by h square, I am taking this 4 pi square to the numerator. 4 pi square is equal to n square pi square by a square. Pi square and pi square in the LHS and RHS get cancelled off, and I get E is equal to n square, h square is taken over RHS. I have a square here, 2 into 4, 8 and m, therefore 8m a square. So since n is available in the RHS, there is a subscript given for E called as En. That is, n is a quantum number. Here it refers to the values called as 1, 2, 3, etc. If n is equal to 1, we can consider it is at the lowest energy level. N is equal to 2, first excited energy level. N is equal to 3, second excited energy level, and so on. Since it is a freely moving particle, n is equal to 0, this condition should not be taken because it is a freely moving particle. Now, when n is equal to 1, the above equation becomes E1 is equal to 1 square h square divided by 8ma square, which is equal to h square by 8ma square. Then when n is equal to 2, what will be the value? E2 is equal to 2 square h square divided by 8ma square, that is 4h square divided by 8ma square, which is equal to 4. What is this? This is E1. Therefore 4E1 can be written here. Similarly, n is equal to 3, you get E3 is equal to 3 square h square divided by 8ma square, that is 9E1, and so on. So this base equation En is equal to n square h square divided by 8ma square is called the energy value of the particle which is freely moving inside the one-dimensional box, and these values are called as eigenvalues, that is the set of energy values possessed by the particle which is freely moving inside the box. The diagrammatic representation of this eigenvalues can be represented as, here let n is equal to 1, then we can take this as E1, that is E1. Then when n is equal to 2, this can be taken as E2, and then here n is equal to 3, this is taken as E3. Even E2 can be written as 4E1 and E3 can be written as 9E1, and so on. Let's go. In this one-dimensional potential box of width A, the energy is represented, the energy possessed by the particle is diagrammatically represented here. Now, still we have to solve for equation 4. Can you see this? Psi of x is equal to a sin kx. What is the value of k? K is equal to n pi by a. Therefore, substituting this equation 5 in equation 4. In equation 4, you get, applying equation 5 in equation 4, you get psi of x is equal to a sin kx. Kx is n pi by a into x. Now, still we need to solve for this arbitrary constant because the arbitrary constant b is equal to 0 there. Now, I am taking this as equation number 8. To find a value, we are going for normalization condition. That is, normalization is, we need to take the probability density. So the topic is about, we are going to find the arbitrary constant value a. For this, normalization of the wave function should be taken. Normalization of the wave function psi. Since the particle is definitely present inside the box, p value should be taken as 1. We know that the probability density value is 1 when the particle is 100% surely present in the box, definitely present in the box. So P is equal to, for one-dimensional case, the formula is single integral mod psi square dx is equal to 1. What is the limit here? You can find The limit is the width of the box. The particle is limited to move within the box of boundary condition 0 to a. Therefore, the boundary condition is 0 and a. So already we have here psi of x, even I can write it as psi of x. Look at the 8th equation. So psi of x is a sine n pi x by a. Then integral 0 to a mod psi square is a square sine square n pi x by a. Here I have dx, which is equal to 1. So what is probability density? Probability density gives you the particle's position or finding the particle in the given dimension. In this one-dimensional box, it is 100% present. We are finding 1. That is 1 is equal to 100%. The particle is present. It is called as probability density, finding the particle in the given dimension. Now I am going for finding a using this normalized wave function. Therefore, I have a square is a constant, 0 to a sine square n pi x by a dx is equal to 1. We know that sine square theta is equal to 1 minus cos 2 theta by 2. You can see this equation here. This is considered as theta. Therefore, sine square n pi x by a, I am writing it as 1 minus cos 2 theta. That is, theta here is n pi x by a by 2. So substituting that here, we will get a square 0 to a 1 minus cos 2 n pi x by a dx is equal to 1 divided by 2. I am taking this 2 over a square by 2 here. Then solving this, we get a square by 2 integral 0 to a dx minus a square by 2 integral 0 to a cos 2n pi x by a dx, which is equal to 1. Now on solving, we get a square by 2 x 0 to a square by 2 sine 2n pi x by a divided by 2n pi by a is equal to 1. But we know that sine of n pi is always 0, so the second term vanishes. Therefore, we get only a square by 2, then substituting a here, which is equal to 1. A square is equal to, here I am writing, rearranging this, you will get 2 by a. A is equal to root over 2 by a. So I will get 2 by a with a square root. Substituting the value of a is equal to root of 2 by a in this equation. In this equation 8, I'll get psi of x is equal to, or even I can write it as psi of x as psi of n is equal to, a can be replaced with this value 2 by a sine n pi x by a. So this is the wave function value of the particle which is freely moving inside the one-dimensional box. When n is equal to 1, psi 1 is equal to root 2 by a sine 1 pi x by a. Similarly, psi 2, that is when n is equal to 2, we get 2 by a sine 2 pi x by a. Similarly, for n is equal to 3, you get root 2 by a sine 3 pi x by a, and so on. So diagrammatic representation for these wave functions, that is, these are called as the set of wave functions for the particle moving freely in the one-dimensional box called as Eigen Functions. Previously what we have determined here is set of energy values called as eigenvalues. Here eigenvalues, here set of energy values En, here set of wave functions called as Eigen Functions. Now when n is equal to, even you can consider n is equal to 1 here. For E1 you will get the wave function psi1 is in this one. And then when n is equal to 2, the energy values 2, it is psi1. Now you are going for psi2, then it is psi2. Similarly, when n is equal to 3, for energy E3, here you are going to draw it for psi3, the wave function psi3, it is here. So this represents the diagrammatic representation of particle moving freely in a one-dimensional box of width a. If the probability density is, what is probability density? Modulus of psi square, mod psi square. Here the diagrammatic representation of mod psi square can be written as or drawn as, here when n is equal to 1, E1 you get psi1 square. When n is equal to 2, E2 you get, because mod psi square will be having positive values, they will not have any negative values. So this is for n3. When n is equal to 3, E3 modulus of psi square. So you get the diagrammatic representation of probability density here. Here a wave function psi, and this is the energy representation. So in this video we have seen the energy values En, set of energy values, and a set of wave functions termed as eigenvalues and eigenfunctions of this particle moving freely in a one-dimensional box of width a.